This will continue our discussion on the frog muscle and nerve. The first video looked at the setup and data collection. So, as a review, we looked at the dissection, we looked at the setup for the sciatic nerve and the gastrocnemius muscle, and then we studied the effective stimulation on the action potential, effective stimulation on muscle contraction, and the effective stimulation frequency on muscle contraction. We've done that before with sciatic nerve, so we'll move on to the discussion part of it. So we'll look at the sciatic nerve first and then talk about the muscle. So sciatic nerve is a mixed nerve. It means it has both sensory and motor fibers in it. The sciatic nerve we snipped at one end and the other, and then laid it in the nerve chamber as we see here. A nerve is a bundle of axons in the peripheral nervous system. Mentioned before that the sciatic nerve has about 1,500 fibers that are both sensory or afferent and motor and efferent. The sciatic nerve in the frog doesn't exactly look like this. This is more of a human type nerve. Interestingly, the frog sciatic nerve doesn't have bundles of axons and fascicles, but this is what we're looking at. And the point of this portion here is there's a lot of connective tissue here, and that's the point I'm trying to make. And if this was a human nerve, you'd have endoneurium, perineurium, epineurium, and even mesoneurium on the outside, holding everything together. So there is some connective tissue in the middle, and that's going to provide resistance to our shocks. Here's a little different view of a human nerve again. And again, each of the little yellow circles are axons, and there are fascicles, bundles of axons that we would look at. Remember that we are not recording an individual action potential. That's what this is. Okay, so if the individual axon, which has a resting potential of about minus 70 millivolts, receives an input of voltage that raises the voltage to threshold. It's about minus 55 millivolts. Once we hit the threshold voltage, we open double-gated sodium channels. Sodium diffuses into the cell, making the deflection go positive to about positive 30. Then those begin to close, potassium begin to open, and we move back down. So the initial phase, number 3, is called depolarization. The going down is called repolarization, and then a little valley here from 5 to 6 is called after hyperpolarization. Okay, so this is when we record both inside and outside electrical difference on the internal portion of an axon. We're not doing that. Remember, we're measuring the external portion of the axon, and we're looking at what's called the compound action potential. Now, one of the things that we've mentioned before, an individual neuron is an all or none event, and the action potential, if you reach threshold, looks exactly the same. Once you reach the threshold on one of the double-gated sodium channels, that provides the stimulus to open the next one, next one, next one. So it sort of falls like dominoes. And the all or none principle tells us no matter where we measure on the axon, that action potential is going to look exactly the same. Okay. Now, we're not measuring that, though. We're measuring what's called the compound action potential. The compound action potential is graded. Graded means the size of the response is dependent upon the size of the stimulus. So the compound action potential is a combination of all of the individual action potentials that have reached threshold. So each individual action potential is all or none, while the compound action potential is the sum total of those. and it's said to be graded. Now, one way to think about the compound action potential is think about banks of lights that you can turn on and off. All right, and so if you can turn a row of lights on or off, like in our classroom, then you have a graded response. The more lights that are on, the more bright the classroom would be in general. So, go back and look at this one. So if you think about this, and again, this is the nerve laying across the wires. Think about this right here. Let me do this. So we'll make this our wire right here. So we're going to go, and here's my wire. Okay. And so the nerve, just like right here, is sitting on the wire. And when we give it a shock, I'll put over here an S. That's the stimulation. That's going to send it down the shock. That shock down the wire. Okay? Now, depending on how big that shock is, let's say it's fairly small, what it's going to do is it's going to deliver and transfer it from the wire, right, in this direction to the neuron. Okay? And each one of these, right, little yellow spots are axons, right? So here's a fascicle, here's a fascicle, here's a fascicle. So there's very, very, very many axons here. And what's going to happen is the ones that are closest to the shock, like right in here, right, those are the ones that get excited first. And as it moves through the nerve and it gets farther away from this wire, with time and distance, especially because of the connective tissue, that initial shock is going to be smaller and smaller. And by the time it reaches the further nerves, it's not big enough to have the individual action potentials be generated because it doesn't reach threshold. And so that's why we see initial small response, and it gets bigger as we recruit more fibers, and bigger as we recruit more fibers, and bigger as we recruit more fibers, and eventually we have them all recruited. Once they are all recruited, the response doesn't need bigger, because once you have them all, you can't have any more. And so that's kind of the way to look at the compound action potential. It's the sum total of all the active axons within the neuron. So we'll go back to where we were before, kind of look at the data. So this top one for this data collection recording is the stimulus. This blue spiky kind of looks like the stimulus artifact. And then this blue thing here, that's my compound action potential. So my compound action potential, right, what I would do is I would highlight basically from here to right here, and would tell the computer this is my compound action potential between those two spots. What the computer does is it picks the highest spot here, it picks the lowest spot here, and actually measures the distance for us here to here. It's called a P to P, and then displays it right here so we can read it. Okay? And what happens over time is when we have a small voltage, we don't see anything. So I'll just kind of draw it right here. So a small voltage, it looks like that because there's no response. And we increase the voltage a little bit, and eventually we see the first response. That's called the threshold voltage. And you'll see something that looks like this. Okay? And then as you increase the voltage, you get a response that looks like this. And then eventually it might look like that. So you see bigger and bigger responses as you give more and more voltage. So we say this is graded because the size of the response depends on the size of the stimulus. So the compound action potential is a graded event. So looking at the data, okay, we sort of saw this data before, we see that at 0.2, we saw the smallest response. That was the first one. That was our threshold voltage. We explained that before. That's the smallest voltage that elicits a response. At 0.9, The response was 0.0133. That was the maximal response, because above that, it doesn't get any bigger. And then we can use those two to reference other things. Below threshold is called sub-threshold response, right? There should be no response for that. Above maximal is called supramaximal, and supramaximal is going to give us the same response as maximal because we have all the muscle fibers recruited. And then between threshold and maximal are the submaximal ones where we have the graded responses. So I explained the subthreshold, threshold, maximal, submaximal, and supramaximal definitions already. We did on the last video as well. So the compound action potential represents spatial summation. Summation is an increased response. That's any type of summation is increased response. And spatial summation refers to an increased response due to an increase in the recruitment of active units, that more axons, more nerve fibers, if you will, are becoming active. So we have a greater stimulus, we have more fibers, we have a bigger response. Okay. Spatial summation is occurring here because we're giving a single separate stimulation. So I only have one stimulus, I can't have a frequency response, and we need that to have the other type of summation we worry about, temporal summation. So this is spatial summation because it's a single response. Okay. The other thing that we looked at, and we have some data that will show it, is what happens with lidocaine. Okay, lidocaine, novocaine, procaine, those are all local anesthetics, and they're used in especially emergency medicine and dentistry as a local anesthetic. What it does is it blocks action potentials by blocking sodium channels. So in the other video, I explained a little bit how you need to reach threshold and open double-unit sodium channels, so sodium comes in, and that basically causes the action. That is the action potential, I guess is the best way to say it. So if I block sodium from entering the cell, I'm going to block the transmission of an action potential, so you can't feel pain because you can't interpret it because there's no signal. Okay. What's interesting about the cane family, so lidocaine, procaine, novocaine, is at low doses, it's specific to the small unmyelinated fibers. Those are the ones that are called nociceptors, not all of them, but many of them, that carry the pain sensation. And so if you can't interpret pain, you can't feel pain. And if you can't send the pain signals, you can't feel pain. And so that's what those things do. And, think about, especially in the dentist's office, if they gave you a dose of, Novocaine that literally caused everything to be blocked, then you wouldn't be able to swallow or move your mouth. And that would be bad in terms of the procedures. So by being able to preferentially block the smaller fibers that carry pain, it's a very effective way to treat, fill cavities or give someone stitches or, other things they use for, lidocaine. The skeletal muscle part of this is initially very similar. And so you sort of need to understand the first one to understand the muscle one. And if you look at it, it's very similar. So just like the nerve is a bundle of axons in fascicles, and we measure the total response of all of the individual axons called the compound action potential. In the muscle's a bundle of muscle cells in fascicles, right? And when we measure the muscle response, we're measuring which muscle cells get excited and help add to the contraction of the muscle. So in many ways, it's analogous to what we do for the compound action potential. So here's a picture of what our setup looks like. We have our frog with the leg pinned down, still attached at the knee. The gastrocnemius has been isolated and the Achilles tendon excised. We have tied some sort of thread from the gastrocnemius muscle distal end to the force transducer, where we can measure the force or the strength of contractions. These red wires go to the stimulator. There are pin electrodes into the muscle belly. If you shock the stimulator, it shocks the muscle contracts, so it shortens in this plane. That pulls on this. There's a little, in this little eyelet, there's a spring that compresses the spring and sets up a voltage, and that's read as a change in muscle tension on the computer. And what we're going to do initially is we're going to stimulate with one shock, just as we did in the sciatic nerve, and we're going to observe the response, which for the muscle would be a twitch. Yeah. So here's an example. Here's my stimulus here. And then here's my muscle response and tension. You see that again, these triangles are the event markers. In this case, it's recording the actual stimulus. So here's the first stimulus, and notice right here, no response. Here's the second stimulus, it's bigger, no response. Third stimulus, oh look, I see a little response. This is my threshold voltage, right? I don't know what this data is, it's not mine, but we can look across here and go, okay, this looks like it's probably 0.2 volts. All right, no response. This one looks like it's 0.3, no response. This one looks like it's 0.4, and I see a response. So this would be my threshold voltage. Then we give 0.5, and it's bigger. Give 0.6, and it goes up to this high, and we'll give 0.7, so yeah, it's bigger, and it's the same response. So that would be our maximal response, after which it didn't get bigger. This last one here, that's just as big as maximal, would be supramaximal. And then the one data point between threshold and maximal would be called the submaximal. Again, we'd have similar data, but instead of measuring the voltage of the compound action potential, we measure the maximum muscle tension of the individual twitch. And you can see 0.4, and this data right here shown here is not this data in the table. But my threshold voltage was 0.4. That's where we first saw the response. And then above 1.2, it never got any bigger, so that was my maximal. All right, so this is kind of a way to look at this and go over those voltages again. So let's look at a couple voltages. We'll do 3, 6, 9, and 1.5. So 0.3, 0.6, 0.9, 1.5. I won't do 1.2 because it's right there. So if we stimulated this muscle with 0.3 volts, what would the response be? So I look at my table and said, oh, the stimulus voltage, the threshold is 0.4. 0.3 is below that, so we'd be in the sub-threshold range. By definition, a sub-threshold stimulus would give me no response. So 0.3, no response. 0.6 is between 0.5 and 0.7. So that means my response would be somewhere between 19 and 31, right? So probably somewhere around 25. So my response would be about 25 grams of tension at 0.6. At 0.9, that's between these, right? And so at 0.9, it's somewhere between 48 and 61. So I would say 56, 57 would be 0.9. That would be my response there. And then 1.5, we look here, 1.2 is my maximal. Anything greater than maximal is called supramaximal, right? And at supramaximal tension, I should get the same response I had before. So that should be 72 grams. So that's kind of one way to look at it, interpret those numbers and apply them. Again, this has all the definitions we've gone over before. And what we're doing is as we increase the amount of stimulation, we're getting more and more active units as they move further away from the source of stimulation. We start to reach threshold for the other muscle fibers, and eventually we'll see the maximum when all the muscle fibers are recruited. Just like the compound action potential, this is an example of spatial summation, an increased response due to an increased recruitment of active units. So if we have a greater stimulus, we have more fibers active, and we have a bigger response. This is said to be graded. The muscle twitch is said to be graded, again, just like the compound action potential, between threshold and maximal. We looked at this and the muscle twitch in the last video. As a reminder, the muscle twitch can be divided into three sections. The latent period, which is the delayed period between the shock and when you actually see tension develop. When tension starts to develop to the peak, that's called the contraction period or contraction phase. And then from the peak back down to rest, that's called the relaxation phase. So the muscle twitch can be divided into three phases: latent, contraction, relaxation. So there's the definitions that we just explained. So you don't have to know this detail, and we went over it in a previous video a little bit. Latency period is when you have the nerve action potential, which then results in a muscle action potential. And here's that again, that wave of electricity going in, exciting the DHP receptor, open these calcium channels, calcium diffusing out and allowing the cross bridging. So notice here, the myosin heads aren't physically touching the actin because of these little string-like tropomyosin, right? It's preventing that. But as soon as we move tropomyosin out of the way, then we can actually get tension and start to develop contraction. Right? There are two things you need for relaxation here. You need to put ATP on the myosin head so it releases, and the tropomyosin slides back in the way as an inhibitory protein. And you need to take the calcium, these little green dots here, and you need to actively pump them back into the storage sacs. Okay, so that's called resequestered calcium. That has to happen as well for relaxation. Now, one of the things that happens is if you have more calcium, you'll make more cross bridges, which means you'll have more tension, you'll have greater strength. Okay, we're going to see that again and again in looking at the data. So the muscle twitch is an example of spatial summation. It's graded between the threshold and maximal levels, and the size of the stimulus determines the size of the response. Once we establish what the maximum tension is at the maximal voltage, we can use that to recruit all the muscle fibers and then change the frequency of stimulation and look what happens to the prep. Now, this isn't great data here. It's not bad, but it's not great. These should go up a little higher. And, you know, if we start here, we're starting stimulation about, 23 seconds. And so we go a full half minute here as the muscle starts to fatigue. So sometimes I like to go a little faster because you should see this continually go up. So we'd expect this to be more along this line. So we'd expect it to do something like this. And so it would do this, and then it would start to thin out, get thinner, 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 and then eventually become a straight line. So this is because we've increased the frequency, right? Summation, right, means bigger response. So since we increase the frequency, we have what is called temporal summation. Temporal summation. Okay? And we're going to divide this into three different areas. And those three areas are going to be trepe, wave summation, and tetanus. Now, what each one looks like, I'll kind of draw a quick little summary of each one. Now, by definition, the twitch is a single muscle response to a single stimulus. We've seen that before. It goes up, it reaches peak, comes back down. That initial phase before we start to develop tension is the latent period. From the tension development to the peak, right, is the contraction period. From the peak back down is relaxation period. The twitch is the twitch. We've sort of talked about it. So let's look at, because it's a single muscle response to a single stimulus. It's not part of the temporal summation. So when it says no summation, right, that's not true. There's spatial summation, but there's no temporal summation for that. Okay. So the first thing we're going to do is, okay, we set this to maximal tension, right? And so if we look at our data from before, it was, what was it, 1.2, right? So we saw that our maximal tension was 1.2, and then we turn on the stimulator and we continuously stimulate the muscle, the gastrocnemius muscle, and increase periodically the number of hertz. Hertz is cycles per second or pulses per second. So it's how many times in a second do we stimulate the muscle. In the gastrocnemius muscle, normally at 1 pulse per second, so stimulate it once every second, is enough time for the muscle to contract and then completely relax, reset, and then just do that individually. But as we start to increase the stimulation frequency, you see something looks like this, okay? So you see that the responses are closer together because the frequency is higher, and you see that it steps up. I'll go all the way down, sorry. We'll see that it steps up here, okay? As it steps up, it looks kind of like a staircase. So use black. So we start here, and then we go up here, and then we go up here. Looks like a staircase. So this is called treppe. Treppe is a German word for staircase. And so the question is, why does this go up? Well, it goes up because of the increased availability of calcium. And so when we looked at the slide a little earlier, we mentioned calcium diffuses out of the sarcoplasmic reticulum. We open that calcium channel by the DHP dihydropyridine receptor, and calcium diffuses out. Now, to get relaxation, we have to resequester that calcium. We have to take that calcium out of the cytoplasm and put it back in the storage sac, otherwise it will cause contraction. Well, what happens is there's not enough time, because we have a higher frequency, to put all the calcium back where it was stored before the next contraction comes. So what happens is you already have a little bit of calcium floating around because you didn't have a chance to put it all back. And then the next contraction comes. And now we release the same amount of calcium we had before, plus we have a little extra that was there. And now we have more calcium. We have more calcium, we have more cross bridges. We have more cross bridges, we have greater strength. So each little wave, right, that goes up is due to the increase of calcium within the muscle cell itself. Okay, so the first thing, treppe, is due to one thing, the increase in calcium. The other thing to note is treppe, right? Black. Goes back down to baseline. So notice we go back down to baseline there. That's an important consideration for it to be Treppe. Right? So it returns to baseline. It subsequently increases force due to the increase in calcium concentration, because you can't put it back into the storage sites fast enough before the next contraction comes. Now, the next phase, as we increase the frequency, is wave summation. It's going to kind of looks familiar, but it's got one major difference. So I'm going to draw it a little higher, if I can, and it's going to be a little faster. So in many ways, right, it looks like Treppe, except there's one major difference. And that major difference is we don't go back down to baseline. So notice that we still have the little contractions and they step up. But this time we don't go back down to baseline. That's the big difference between Treppe and wave summation. Treppe goes to baseline, wave summation does not. The good news is because they look similar, partly because they are. And so one of the major reasons why we have wave summation is the increase in calcium concentration. Because the frequency of stimulation is even faster, we don't have enough time to resequester calcium to put it back where it was stored. So there's even more calcium accumulating inside the cell, which makes more cross bridges, which gives us more strength of contraction. But the other one has to do with the difference between Treppe and wave summation. Whenever we contract a muscle, we have to stretch it first. And we have to stretch what are called the series elastic elements. So the series elastic elements are your tendons and connective tissue. So I'm just going to underline it right here, series elastic elements. Sometimes it's just called the SEE for series elastic elements. And series elastic elements, we have to put energy into them to stretch them first so that the muscle can actually contract and shorten. And in real life, some of our energy for contraction goes into stretching those things. But if they're already stretched, I don't have to put as much effort into it, which means I have more energy to go into contraction, which means the contraction strength gets greater. So wave summation is due to two things: the increase in calcium concentration and what we call the pre-stretch of the series elastic elements. And that's only going to occur when you don't go back down to baseline, because the muscle is partially stretched, which means I don't need to put as much energy into stretching, so I have to do less of that, which means more energy can go into actually developing contraction strength. So that's wave summation. And as we keep going, the last one looks like this. It's not as good a yellow, I guess. So it has the highest, it has the highest contraction strength. And because the contraction strength is so high and the frequency is so high, it's just flat on the top, okay? So it doesn't have little spiky things, it's just flat. This is the highest contraction strength. This is at the highest number of hertz, so this is 10 to 18 hertz or cycles per second. All right, good news is it looks a lot like wave summation. So, not surprisingly, there are two things that cause it: the pre-stretch of the series elastic elements and the increased availability of calcium because of the high frequency. But the third thing, tetanus, has a third thing associated with it, and that's a little different. That's called tonic muscle recruitment. Now, you probably didn't learn about tonic muscles in your anatomy class. Tonic muscles are voluntary muscles that are slow to contract and slow to relax. and they looked very similar to smooth muscle that's under voluntary control. We don't study it in human anatomy courses typically because humans don't have very much of it. We know it's in the orbicularis oculi, that's what you do to close your eyes, and then your sphincter muscles, which help keep the contents of various places in your intestines or bladder so that things don't leak out, right? So that's a nice thing, but in both those cases, tonic muscle is, sometimes it's called non-twitch muscle, but tonic muscle is designed to have these nice long contractions. So they're good for prolonged contractions. And what's interesting in the frog, gastrocnemius, is the frog gastrocnemius has a little bit of what we call tonic muscle. So it's at the very bottom, so it's hard to see, but tonic muscle. Now, tonic muscle is in the frog gastrocnemius. And so what's interesting about tonic muscle is it's not recruited. It doesn't become active until you have a high frequency of stimulation for a very significant time period, at least physiologically. So usually it takes, a high frequency, at least 10 hertz, to stimulate the tonic muscle. And it's slow to develop tension and slow to relax. So what happens is that when you're doing this experiment, usually the tetanus jumps up even more because of that recruitment of tonic muscle. So technically, tetanus is not strictly temporal summation, it's also spatial summation. Because we have that word recruitment, which means we have more fibers active. So that fits. So tetanus is due to three things: the increase in calcium concentration, the pre-stretch of the series elastic elements, and the recruitment of tonic muscle, which only occurs at a high frequency. So here's kind of, if you look at it this way, it's not too hard to remember what's going on here. For temporal summation, right, the three forms of temporal summation are trepe, wave summation, tetanus. Now, trepe is the first thing, and it's got one thing associated with it, and that's the increase in calcium concentration. It steps up, and the responses get bigger subsequently, and it goes back down to baseline. So that's trepe. Wave summation is between 6 and 10 hertz. It's due to the increase in calcium concentration, and then the pre-stretch of the series elastic elements because we don't go back down to baseline, right? So right here, there's all that distance right here where we don't go back down to baseline. So that's wave summation. So the second thing is due to two things: the increase in calcium and the pre-stretch of the series elastic elements. The last one is tetanus. Tetanus is that flat line that will develop the highest tension, right? And that's due to three things. We'll just add one more thing. So the increase in calcium availability or concentration, the pre-stretch of the series elastic elements, and then in the last one, it's the tonic muscle recruitment. So the first one has one thing, it's calcium. We add one thing in the second one, it has two things, calcium and pre-stretch. And the third one, we add one more thing, it's got calcium pre-stretch, and then the tonic muscle recruitment. So that's what we see with temporal summation in a frog. In temporal summation, we see an increase in the activity of each unit, so it's an increased frequency. And remember, the one word thing to remember for temporal summation is frequency. For spatial summation, it would be recruitment. And since we're using the maximal stimulation, it means the temporal summation is observed here, except for that kind of strange case where frogs have in their gastrocnemius some of that tonic muscle. If we had done that with humans, as an example, we wouldn't see that because humans don't have tonic muscle in their gastrocnemius. So that's the temporal summation. And the nice thing about this experiment, when you kind of break it down this way, is the first part, as we increase the voltage, right, to increase the number of active units to measure the twitch tension. That was called spatial summation. For the second part, where we increase the stimulus frequency to increase the response, that is called temporal summation. So unlike the EMG lab, where we couldn't differentiate between spatial and temporal summation, in this lab it's fairly easy to do based on our stimulating parameters. So that wraps up the skeletal muscle and nerve action, compound action potential for this lab.